Hello, good afternoon, everyone. While you log in, I will start sharing my screen. No, perfect. So good afternoon, everyone, and welcome to this joint ETIP Ocean and Ocean Demo webinar. So this is a collaboration of these two projects. ETIP Ocean is the European Technology and Innovation Platform for ocean energy, aiming at accelerating the sector's process by bringing stakeholders together and sharing knowledge and expertise, such as in this webinar. And Ocean Demo is a project funded by Interreg Northwest Europe, and our speakers today are indeed were indeed enabled to demonstrate thanks to this Ocean Demo project. My name is Lotta Pirttimaa. I'm a Senior Policy Officer at Ocean Energy Europe, who are coordinating ETIP Ocean and held by Technalia, who are leading the work of the technology research and innovation of the ETIP Ocean project. Now, next slide. Okay, so with ETIP Ocean, we have organized several webinars, and you might have noticed that this there has been a short, let's say, gap this year, and that's because our project supporting ETIP Ocean ended at the end of last year, and now starting from August, we have started the new project that is supporting the activities of ETIP Ocean. So now we are back up and running with these ETIP Ocean webinars as well. And I just wanted to clarify here that the new project supporting both ETIP Ocean and the set plan implementation working group secretariat, which is called Ocean Set, is this project supporting both these activities called ETIP Ocean. So now we have these two initiatives under the same European funded project. So in the future, you'll receive invitations to our further webinars, so we will continue with these technology-focused webinars and also on consenting and environmental impacts. So look forward to those invitations. And in order to get those invitations, I strongly recommend you subscribing to our newsletter on the mailing list on our website, etipocean.eu. You will also receive information about sectoral events and consultations that we do. So we would be very happy to welcome you on board. Now, today, the topic is really what lessons learned from wave energy deployment. So we did an earlier webinar, I think it was last year already, with Ocean Demo as well, on a tidal demonstration, and specifically focused on arrays. And with Wave, we are looking into the demonstration that Mocean and AWS have done under Ocean Demo. And this is an important topic because real sea demonstration is really a very invaluable, important way of demonstrating technology, reducing costs, and then paving the way to the next stages and towards commercialization. So here you can see today's agenda. We have first an introduction from Pablo Ruiz Minguela from Technalia, who will explain the scope and the background of this webinar and the topic. And then we have, as I mentioned, projects from the Ocean Demo project, Chris Retzel, the founder of Mocean, and Simon Gray, the CEO of AWS. And at the end, we have time for questions, and you can put your questions in the Q&A box during the presentations. And also, if you want to share your own experience with demonstration or testing, feel free to write it down in the box. I can read it out loud and we can have a discussion about it. So it doesn't have to be specifically a question. We'd be happy to hear also your own experiences. And with that, I will stop sharing and hand it over to Pablo. Thank you.
Thank you, Lotta. I suppose that you can all see my screen.
Yes.
Yeah, okay, perfect. So good afternoon, everyone, and thank you for this brief presentation on the webinar, Lotta. Now we're going to make a short introduction to the strategic research and innovation agenda for ocean energy before listening to other speakers. The SREA is a reference document for the whole ocean energy sector and gives specific inputs to public bodies, including member states, for inspiring R&D calls. For example, we can see some inputs taken directly from the SREA in the Horizon Europe calls that has been launched recently, and the new ones that are going to be launched really soon. The report has not been produced from scratch. It's an update of the previous strategic research agenda produced in 2016, and the main driver for this update was achieving ocean energy commercialization. With this purpose, we tried to involve as many sector stakeholders in the process as possible. The SREA was officially launched in May 2020. Now it's publicly available at the Knowledge Hub of the ETIP Ocean website. You have the link there where you can download or go directly to the website. The Strategic Research and Innovation Agenda has been developed in the context where ocean energy can play a crucial role in meeting the European Green Deal objectives and a 100% decarbonized energy system. Different European strategies are behind these objectives, such as the strategies on offshore renewables, industry, SMEs, or biodiversity, among others. We believe that ocean energy can be the next big thing in energy. The SREA includes a chapter which quantifies the effort on research, technology development, and innovation needed to move forward this sector. 1 billion euros should be mobilized from 2021 to 2025, from which approximately one third will come from private investment. Due to the large development of ocean energy technologies, 70% of these funds should be devoted to demonstration, pre-commercial and industrial rollout actions. The challenge areas represent a set of the research and development fields that the ocean energy sector has identified as the most worthy of investment during the next period of 4 to 5 years. After a prioritization exercise, the ocean energy industry and research professionals agreed that the design and the validation of ocean energy devices is the most urgent and crucial area to focus on. Other challenge areas, therefore, are aimed to support this one, including foundations, connections, and moorings, logistic and marine operations, integration in the wider energy system, data collection, analysis, and modeling tools. A similar prioritization exercise was conducted for the identification of a number of priority topics per challenge area, according to the opportunities for the sector in Europe and the urgency to overcome. For this priority topic, the SREA defines the scope, the applicability, the actions, the expected impact, the TRL, both entry and exit levels, and the budget required, with a reference to the number and size of the projects. Today's webinar explores as Lotta has said, the lesson learned from wave energy deployments, and it's framed within the topic demonstration of ocean energy devices to increase experience in the real sea conditions, which takes part of the design and validation of ocean energy devices. This priority topic, the demonstration of ocean energy devices to increase experience in real sea conditions, aims to validate the cost effectiveness, reduce the risks, and attract investors to future commercial projects. In particular, long-term deployments is necessary to provide all the information to define the performance, reliability, availability, maintainability, and survivability metrics. So that's a critical activity. Thank you very much for your attention. Now it's time for the other speakers to share their experience.
Thank you very much, Pablo. And without further ado, I will give the floor to Chris from Mocean.
Well, good afternoon, everybody. I hope you can see my screen now.
Yes, we can see it.
Perfect, thank you. Move into presentation mode. Thank you for the introduction, Lotta. I'll just move straight into my presentation. So this is BlueX. This is the machine which we tested in Orkney, assisted by Ocean Demo's funding. So I'll just briefly go through the milestones on the right-hand side here. But in 2019, our BlueX design was accepted by Wave Energy Scotland for Scottish government funding support, and we commenced build in 2020. And in 2021, we shipped to EMEC, to the Scapa Flow site, where we carried out tow trials. And then in summer, we started the power generation and spent 5 months at sea. Our technology backstory. So it started with computer models and physical models. And here on the left-hand side, you see some schematics of some hinged rafts that we tested numerically in the first instance. So these are very simple bodies. At the top there in blue, you see a symmetrical hinged raft with a joint in the middle, and those two sides, those two sections, can move relative to each other. And we notionally take off power from that hinged joint. The second one down shows a different geometry, and the third one a different one still. And then the graphs below that show the extracted power. And you can see that the red version, that is the middle geometry, has the highest output. So we then built that, and we tested it in wave tanks, and that helped us validate our early numerical models. Well, we then moved on from that into devising other geometries, and you'll see the little graphic in the bottom left there displaying hundreds of different geometries, which were then tested in the same way. So we take the geometry and we put it in a numerical wave tank, and we determine the amount of power that it can absorb. And the amount of power is dependent on the geometry. So you need to explore a very large number of geometries in order to determine which ones are best. And the constraints are the mass of the machine, how much it weighs, because this is a good proxy for the cost of the machine, and likewise the torque of the power takeoff, which is in that hinge. We run AI optimizations around that. So these are examining all those different geometries and breeding them and mutating them, and they converge on a final product, which in this case we see in bottom right, and we're testing this particular shape in a wave tank. And this provides further validation of our numerical models. And top right here, you see the two wave energy converters compared. So on the bottom there, the bottom gray picture is the simple symmetrical hinge draft, which is just 2 cylinders joined with a power takeoff. And above it, you see our modified version, which is very different. It's asymmetrical. The forward section is considerably longer than the aft section. And it has these deep diving wave channels or plates fore and aft. And here we see a dramatic increase in the amount of power which can be extracted, which is just due to the geometry and the cross-coupling of the various modes of motion. So we were joined into the Wave Energy Scotland Novel Wave Energy Converter Programme, and we took our early work to the programme in our application in 2015, and we won our first grant from Wave Energy Scotland in 2016, and we used that to build the model which I showed earlier. And we further developed in 2017 and 18 in the stage 2 of the NWAC program, the asymmetrical model which you see here. And finally, we received a grant to build the full-scale prototype. So construction took place in Cowdenbeath in Fife, Scotland. And here you see the 2 tubes. On the left, the forward tube in yellow, and then the aft section or a piece of the aft section on the right-hand side. And in the foreground, still in rusty steel and not painted at all, is one of the wave channels, the big flaps front and rear that you saw in the early picture. Here's a picture on the inside one of the tubes. At the far end of the tube, you can see control cabinets. At the near end of the tube in black, you see some battery boxes. We transported those by road 50 kilometers to Rosyth, where on the quayside here, we welded on the forward and aft section of the wave channels. And this shows the winter of 2021 with the wave channels in place and the construction scaffolding still in place and the painting having been finalized. And then we were on the quayside ready to launch. We craned into the water. We needed to ballast the machine so that it would sit right, so that it would sit level and at the right level of submergence. And that's what we're doing here. We're adding water into those white plastic containers until the level is correct. We then removed those containers and added the equivalent amount of steel to the wave energy converter, the WEC, below the water line for stability. We transported again to Orkney and floated the machine out and moored it on the EMEC test site, which is where we did our testing for the next 5 months. So the middle picture here shows you the Orkney Islands and the test site bounded in red in the middle of that lagoon-like area within the Orkneys, which is called Scapa Flow. So Scapa Flow is about 30 kilometers across and about 20 kilometers north to south. And it's pretty well shielded from both the North Sea on the right-hand side of the picture and to the east, and from the Atlantic to the west on the left-hand side of the picture. And consequently, it doesn't really see outside influence on those on the water inside Scapa Flow, but it does see local wind seas, and those local wind seas are of a good scale for us to test in. So 30 kilometers of fetch and a few hours of a good stiff wind gives you waves which can be up to a couple of meters high and of the right period for us to excite the wave energy converter, the Blue X. So here is Blue X out at sea, and Lotta tells me that you're likely to see a rather poor quality video here. The video will play nicely on my screen, but possibly not so well over the web. So let's try it. The view here is of the machine moving in waves. These waves are about a meter or so high. The aft section there is moving relative to the forward section. The aft section tends to move rather more. On the forward section there, towards the top of the picture, there's a tall mast. On that mast are various sensors and a camera. I'll move on to the next picture. I don't know how well that played. I hope it played reasonably well. This is a view from the camera which is on that mast, and we get a bird's eye view of just how steep those waves really are. At the very front of the Blue X, we see some solar panels. These were put there to check their survivability in waves which are as large as this, but also, of course, to see how well they worked as solar panels on sunnier, calmer days. And they worked extremely well. So that was interesting feedback for us. So in the testing, we can control the machine either from the Orkney shore base, which is just a few kilometers from the WEC itself, or from Mocean's Edinburgh or Aberdeen offices. And we can switch it between generation, standby, and maintenance modes. And we do this via a remote user interface, which gives us information about the performance of the machine in real time. So we measure the hinge torque and velocity. So with a torque sensor or a load cell in the shaft of the hinge, we measure that torque, and we also are measuring the rotation rate of the hinge, and the product of the two gives us input mechanical power. Going back to the user interface there, in the middle section, we get the outputs from the generator. So we're measuring voltage and current, and again, the product of those two for each of the phases gives us the output electrical power. And we're dumping that we're rectifying that and dumping it into batteries and storing it. And on demand, we can release that energy into a dump resistor, burn it off, and measure the amount of DC electrical power that we're producing. And we can calculate those efficiencies. We can calculate the electrical and mechanical efficiencies by comparing those readings, comparing those values. And we're also recording the WEC position and heading. The heading is interesting and useful because we correlate that with the wind direction and with the wave directions, which we're measuring with a wave buoy. We're measuring the hull accelerations and velocities because we need to know the loads on the machine. And then there are numerous health indicators, such as the temperatures inside the hull, the humidity inside the hull. And when we go out and gain entry to the vessel, to the WEC, we always check the condition of the air inside. So we are reading gas sensors to make sure that there's sufficient oxygen inside and that there are no toxic gases. So validation, of course, was an important part of this. As I mentioned earlier, during the test program with wave tank testing, we're constantly assessing our numerical models, but doing it at full scale is more convincing and more useful. So the graph on the left-hand side is it's a power table, which is color-coded. So along the x-axis, the horizontal axis, you have energy period, the period of the waves, so from shorter to longer periods. And the vertical axis is the wave height, or significant wave height, HS. And darker is better. Darker means more power. So yellow is small amounts of power, dark green is large amounts of power. And we see that we are getting here up to 5 kilowatts of power. And then on the right-hand side, we have the numerical modeling, which is showing a picture which is very, very similar to that achieved by the WEC. So that gives us a lot of confidence that our numerical models are good. So each one of those boxes represents the mean power for a full half hour. When you look at shorter time scales, you get more power. As I say, we're getting, sustained powers of 5 kilowatts, instantaneous powers of 30 kilowatts. But a key point here is that we were gaining this with just half the generator. We had a generator which was composed of 12 generator modules, and we could connect these all in series to give us high voltages. It turned out, in fact, that the voltages were too high in the very largest Cs, so we had to reduce the number of modules, and we didn't have any more sophisticated method of connecting those models. Had we connected them in series parallel, in other words, we would have had a half generator of 6 modules plus another half generator of 6 modules, we could have generated twice the power. So we proved to our own satisfaction that the 10 kilowatt generator was indeed capable of generating 10 kilowatts. But the lesson learned here, the important lesson learned, was that generator design is a critical balance of torque and speed capability and must be matched to the environmental conditions. So the challenges then relate to this last question, that harvesting wave energy requires adaptation to the high forces and low velocity of waves. And these are very challenging. They're very, very much lower than for wind power and far lower than for power stations on the grid, for which the turbines are turning at 1500 RPM. Well, we're turning at 100 times lower speeds than that. And the consequence is that efficiencies are lower, and it is very hard to generate the amounts of torque that you need without building a large machine. In the picture on the right here, you can see the hinge there, the cylindrical nacelle in to the left of the superstructure there, and that contains that is the size of the generator we're using. So we use a large diameter generator plus a gearbox, and that just suffices for the challenging conditions that we that obtain. I also make the remark here that there's a very wide range of wave velocities because, firstly, of the environmental conditions, which range from flat calms to ferocious storms, and secondly, because the hinge itself is moving back and forth. It's reciprocating motion. So every wave cycle, you see the generator velocity rise from 0 to maximum and back down again. The next step for us, for BlueX, is to move from Scapa Flow, which was relatively sheltered, out to the North Sea. So we can expect then the wave heights will rise by a factor of 3 or 4, and the power harvesting opportunities will therefore be much greater, but the extreme conditions will be very harsh. We've sorted out the wiring such that we can run at these we can run in these large waves at lower voltages. But for onward work, we are very much needing to optimize the generator for these low speed, high torque conditions. And we'll probably move to a new format, a new design of generator, which will be direct drive. It won't use a gearbox, and it will be it will have been optimized for the distribution of velocities that we're expecting. We also continue to evolve the shape of the WEC, and we already have machines which, just by small changes in the geometry, give much improved power outputs. And power electronics also need to be optimized for the range of conditions, the control mechanisms that we need to apply, and for the power factor of the generator. So I'll stop there, Lotte.
Thank you very much, Chris. Just 2 questions from me before we move on. When did you say you deployed BlueX?
We were doing the performance testing from June, so 5 months from June through November.
Okay, so you've decommissioned it now. Okay, yeah, thank you. Okay, so if you have any questions, don't hesitate to put them in the Q&A box and we will take them after the next presentation. So now I would like to give the floor to Simon Gray, the CEO of AWS. Thanks for joining us, Simon. I can't hear you actually.
Okay.
Oh, now I can hear. Now it's fine. It's fine.
Good. Okay.
Good.
Well, apologies for a bit of a mix-up, and apologies to everybody. Due to a bit of a scheduling mix-up, I hadn't actually prepared for this and was 10 minutes late in joining, so I will have to improvise with the presentation. But hopefully, I will be able to give you something which is relatively interesting. I'm going to rely quite a lot on video. The videos are online, so if people want to watch them at high definition later, they can do. Hopefully they'll work, but I'll get on with that and see if I can manage the technology to give us a presentation. So let me share screen. Does anybody know how to do this?
So you should have a share screen button on the bottom of your screen. For me, it's green. Might be
right,
green
yes,
for you.
okay,
Yep.
yeah.
And then you choose the window you want to share.
Okay, right. That I think is the right one. Okay, good. Are you seeing something now?
No, not yet.
That one. And share here.
Okay, it's loading. Yeah, we can see a presentation now.
Good, excellent.
Thank you.
Good. Okay. Guess it actually play. Cool. Well, I will give you a very quick introduction to AWS Ocean Energy and to the wave swing technology, so that you know what we're actually talking about. And then I've got a couple of quick videos of what we've been doing operationally. I'm going to focus much more on our operations than on anything else. And thanks, Chris, for a very educational and informative presentation. And you've given some of the background as to where the test site is and things. So that's excellent for all of us. So AWS Ocean Energy is, sorry, I'm still struggling with technology here. We were founded in 2004 to commercialize something called the Archimedes wave swing. And the original technology was invented by Fred Gardner in Holland and developed by Teamwork Technology. And on the slide, you'll see a picture of the original AWS 1, which was a wave swing built into a large pontoon, being towed out of the Porto Leixões in Portugal for deployment. And that deployment happened in September, October 2004, just after we'd formed the Scottish company to start working on the development of the project. And that machine in the top picture is actually 9 meters diameter and has a stroke of 9 meters and was rated at around about 1 megawatt of peak power. So it was quite a substantial piece of machinery. We narrowly missed having a world first of generating wave power onto the grid from an offshore installation. I think Palamas beat us by 6 weeks. And but anyway, there's a lot of water, a lot of history since then. We are basically a technology development company, so we're looking for technology that works. We're looking for ways of harnessing power from ocean waves, and we looked at a lot of different technologies over the years. And we've learned a lot over the years, and that took us on quite a journey around looking at various other technologies, and then back to the wave swing in around about 2016. And we realized that, and certainly from a personal point of view, I realized that the features of the wave swing which had attracted me when I first met Fred and his partner Hans back in 2004 were still valid, and I still believe it's one of the best ways of capturing power out of the sea. So through the WES program, which Chris alluded to in his presentation, we have designed, optimized, and subsequently built a smaller wave swing at a diameter of 4 meters and a nominal power rating of 16 kilowatts. And that's what you see on the bottom right-hand picture, along with the installation vessel, Green Isle, and the anchor, which is a gravity-based anchor, which the wave swing is attached to, just hanging on the crane on the Green Isle. So what I'll do next is just play you a video of, oh, that's not what I wanted to show you. That's not even that. I'll just give you a quick explanation of how the wave swing works. The wave swing is effectively a submerged canister, and it's in 2 parts. It has an upper part we call the floater and a lower part we call the silo. And the 2 parts move back and forth relative to each other, and they enclose a volume of air which is pressurized, and the air is retained inside the wave swing by a rolling seal which is in between the two parts. You can maybe see my mouse, I'm not sure, but it's just here. And what the wave swing does is it responds to changes in pressure, and those changes in pressure of the outside water are caused by waves going over the top of the machine. So as a wave goes over the top, the water gets deeper, so the pressure increases on the machine, and it pushes the floater downwards. And that has a compounding effect on the pressure, because as we go downwards, we get deeper. But equally, we compress the air inside, and that compression of the air inside matches the compression, the additional depth on the outside. The result of that is we can have a very, very low hydrostatic spring on the machine. And we also have a very low mass in the floater part, which then means that we can achieve a very broad bandwidth in response to the machine. And then with a good PTO, you can control how the machine responds. So other parts of the machine in here, an important part down at the bottom is a big winch with a tether on it. That winch is used, first of all, to pull the machine under the water, and then to regulate the depth of the machine as the tide goes up and down. And we do want to keep the depth of the floater at an optimum depth below the surface of the sea so that it captures wave power, but we don't want it to be surface piercing, because when we see green water loading, and that's not something we want. The rest of the internals of the machine are power takeoff. For this test machine, we used a hydraulic cylinder. That's not something we would want to use in the future. There are some significant issues around using hydraulics in terms of losses and all the ancillary systems that you need to have. So we would like to find a better PTO, but for this particular project, that was what was available to us. So we managed to use it. And indeed, we selected, designed, and integrated this PTO in a very short space of time, and it performs remarkably well in terms of controlling the machine and allowing us to absorb power. It doesn't have a very high efficiency, which is okay for this test, because we weren't looking at efficiencies on the PTO, we were looking at power absorption from the machine. So that's the wave swing, and I think probably the next steps just to show you a quick video of us actually working in Orkney. The first video is our operations of craning into the water and our initial deployment, and then the second video you'll see some pictures from the wave swing actually operating at sea. I'll just pause the video quickly there. At this point, we've towed the machine out to site. because of the way that the various masses and buoyancies are in the machine, it tends to float horizontally, which is convenient for towing, but it's perhaps inconvenient for other things. But what we're doing right here is we're just taking tension on the tether. The tether's been connected to the gravity base anchor, and then the onboard winch will start to pull the machine under the water. All of that's being controlled actually by someone on the deck of the Green Isle. It's probably that person there, and I think that's probably me, using a Galaxy tablet through a 4G connection up to the internet, and from the internet back down to the wave swing via an underwater cable. So we have full control over the machine, and indeed somebody else could be sitting in Inverness in our office, or in San Francisco, or anywhere else they would like to be, and controlling the machine in the same way. Oh, I've skipped forward a page. I'm going to go back. So I've skipped ahead there. Sorry, it was a little mixed up on the videos. But anyway, so this is some underwater footage which we took during deployment. It was late summertime, so the water quality was quite poor. The water's quite warm, so there's a lot of algae in it. But we were able to capture some footage of the machine moving underwater, which is quite nice to see. One of the things we did notice around the machine is that fish are attracted to the gravity base anchor because it forms an artificial reef on the seabed. And so we had a lot of other marine life, birds and other things, which were also attracted to the area, which was quite nice to see. So this was a view of the inside of the machine. And if you remember from the diagram, I showed you where the floater moves up and down. So this middle part here is the bearing column which the floater is attached to, and that keeps the floater aligned with the rest of the machine. And then in the middle here, you can see the power takeoff cylinder. And this was actually filmed concurrently with us absorbing about 10 kilowatts of wave power. The sea state outside on that day was 1.6 meter HS, and a period of well, it was a TZ of just over 4. So it was not quite as wild as Scapa Flow gets, but it was getting there. But the wave swing worked very well, and I'll just continue with this. And this part of the video here shows one of the best bits of instrumentation we put in the machine was this M20 nut hanging on a string in front of one of the cameras, and that allowed us to see whether the machine was still upright and how much it was moving. Yes, we did have pitch and roll sensors which we could look at through the user interface, but actually looking at a nut on a piece of string gave us a much better feel for what was really happening. And the conditions which this was filmed under are probably similar, I believe, probably even a little bit wilder than the conditions that Chris was showing you earlier with the waves breaking over the top of the Blue X. But when I restart the video, you'll see that this string hardly moves, and that's the big advantage of being subsea and using a subsea technology, is that you just don't see those big breaking waves and effectively get bullied in the same way. And that allows us to keep on operating at much higher sea state levels when other people may have to shut down. And indeed, if we started to see too much wave force because of the height of the waves, what we can do is to operate the winch ourselves lower in the water column, and that reduces the incoming wave force and allows us to continue operating in pretty much any conditions which are available, and certainly any conditions which are available in scalper flow. So. Just pause again there, just at the end, where you can actually see the wave swing under the water there. It is when that was taken, it was 3 meters below the surface, but being painted yellow and looking down with the drone, you can see it really quite easily. But it does give you an idea of the scale, and actually the scale which is not very large. It's quite a compact and handleable buoy. And it has the ability to generate a large amount of power. So we're very pleased with that outcome, and we're very pleased with well, we can't claim to have demonstrated survivability because we haven't seen survival conditions; they just don't occur in scalper flow. But we have seen that in what appears to be rough weather outside, it's extremely calm inside the wave swing. Apologies, I'll try and get the presentation to advance.
You can probably use your arrow keys on the keyboard.
Yeah, trying to do that. So there we are. So in terms of lessons learned, there were quite a few and quite surprising ones, and I've really just kept this to again, because I'm going to think on my feet, not being quite ready for this. What do we really learn from the test program itself, rather than from the build phase or from the modeling or from the tank testing or any of the other things? And there were a few things that really came home to us. And one of them was, and I suppose in terms of things to share with other developers, was the true cost of marine operations. So we deployed and retrieved the wave swing, I think, something like, well, we did 3 deployments, so we had 6 operations in and out. We became very slick at the crane ops. We knew exactly how to do it. The team and the crane drivers and the riggers and everybody did these operations several times and got really good at them. The crew on board Green Isle got very good at what they were doing. And so we were able to, when we arrived at site, we were able to get an install done in under 2 hours. And probably less if we continue to refine the operation in the future. But the long and the short of that is that you have, if you have a WEC which requires to be lifted horizontally, as ours does, and indeed as I think pretty much other WEC that I've ever seen does, you need 2 cranes. You need to mobilize these cranes. You need to hire them. They have a rate which they charge. And which they could be charging to other customers. So that's a fixed cost. And for us, it's somewhere just under £10,000 every time you lift the WEC into or out of the water. And the second cost is the marine op. And again, vessels are hired by the day, not by the hour. And so, you get your crew, you get your vessel, and you do the operation. Fuel is expensive. And again, we managed to get these operations down so that we're somewhere just under £10,000 for the marine operation. But between the two of them, that's £20,000 for a deployment or £20,000 for a recovery. Lots of people said, yeah, but we'll own our own vessels. We'll do lots at a time. But the reality is vessels cost what they cost. They don't get cheaper because you own them yourself. A vessel has an opportunity cost. So if you own your own vessel, you can, if you decide to rent it yourself for half of what you would rent it to the market, that's a pretty crazy business strategy. So you have to recognize that deployments and recoveries cost money, and therefore you've got to be able to design that out. But you know, with the best will in the world, a reciprocating machine is going to need at least one intervention a year. So that's going to be a fixed cost.
I'm sorry, Simon, we're running a bit behind the schedule. So if you could wrap up so we can take some questions.
Yeah, sure. Okay, weather, we spent, I think, 8 weeks in Orkney. And out of that, we had 3 days when we could do marine operations. That was a big delay. We could have saved a lot of money commissioning ashore, but a lot of the systems were not capable of being commissioned ashore because we didn't have the right conditions. We had to have the WEC in the water, for instance, to support the floater. One thing we found, we always planned to do actually at-sea access for small repairs and maintenance. But when we did the health and safety cases on it, we found that simply wasn't acceptable. It may be to others, but certainly for AWS's health and safety policy, we couldn't find a way where we could access the WEC at sea safely when you consider the confined space operations, the requirements for rescue, and all of the other things that you have to be able to do. And we don't see that changing for future designs. We had to make a lot of changes to the machine as we went along, and designing for operations right at the beginning is really important. I mentioned earlier that Scapa Flow doesn't provide survival conditions, so if WEC developers are thinking about going there, you either have to have a WEC, which is something like 8th or 10th scale, or you have to go somewhere else if you want to test for survival. Positives, wave swing exceeds the numerical model predictions, and that's really, really good. It also follows the numerical model prediction. So when we predict something out of a particular sea, we get the same loads, the same motions, and a little bit more power than we thought, because I think in the models we'd overestimated the losses. And one thing we did find difficult in Scapa Flow was wave conditions are not all that stable. You may get a wind blowing, but you don't get the peaks of that. And again, we were looking for it blowing at 40 knots in order to generate sufficient waves to be really interesting. But those conditions don't last long, and they don't last long from the same direction. So trying to find a half-hour period where you had stable conditions where you could do justice to measuring the power from the machine was a little bit difficult. So we tended to assess power over shorter periods when we could see that the waves had been stable in a certain set of conditions. But overall, it was a really good experience. We had excellent support from EMEC, excellent support from all of the contractors, particularly Heddles and Green Marine in Orkney and Alphic Shore-Based Services. And yeah, it's been a really, really useful project to us, and you know, lots of lessons learned. So thank you very much.
Thank you so much, Simon. A very good presentation, although improvised. Who could tell? We now have some time for questions, and because we started a little bit late, I suggest that we go 5 minutes over the hour. If you don't have time to stay, the recording will be made available on our website, etipocean.eu, so you can check the rest of the questions in the recording as well. So Simon, if you could stop sharing the screen, should be in the bottom.
Stop share, yeah.
Thank you. And I'll start with the first question, actually, for you and Chris. So Chris, you can come forward as well. Turn on your camera. So could you share some lessons on reliability, maintainability, and survivability issues experienced at sea during the demonstration?
Absolutely. So survivability, as has been said, it isn't possible to check this in Scapa Flow because the waves are not large enough for our respective machines. But what I can say is that we have proven the survival case for the Blue X in wave tanks and shown that the maximum angles that you get at the hinge can be accommodated by the range of the hinge. And in the video that I showed, I don't know if it was apparent, but you do get white water over the top of the machine, so you get inherent load shedding. So in the performance waves, you're able to generate power. As the wave height increases, you start to shed a little bit of the forces, and in the very largest waves, the machine is you can't resist the force of the waves. You have to go with the waves, but the machine is able to flex as much as it needs to. Again, the point was raised about by Simon about the cost of marine operations. So in fact, we only retrieved Blue X once during the 5 months. Other times we handled small issues by going out with a rigid inflatable boat and gaining access during calm periods to the interior of the machine. That was fine. Maintainability was addressed by that, so that in light conditions you can access, in heavy conditions you don't access, and if you do have serious issues like failure of the machine, then you would have to retrieve. But we didn't have any failures of the machine. We did retrieve, but only to make the modification that I mentioned to the power takeoff of adjusting the voltage range.
Thank you. And the same question to Simon. So lessons on reliability, maintainability, and survivability during the demonstration.
Good. Well, I won't repeat what I said about the survivability thing, other than the observation of and we were surprised at how little movement we saw inside the wave swing when in the largest waves. And we did have some storms. I think it was some point in September we had a sustained well over 40 knots for sort of 12 hours or so. So we got about as big waves as we might expect there. But again, we saw pitch motions of under 5 degrees, and that showed that the strategy of being beneath the waves, whilst it brings some challenges, it certainly brings you some advantages in terms of being where the waves are quietest during a storm. Maintainability. My comments about at sea access. Everybody has a different view on this, and our situation is very slightly different in that we can bring the machine to the surface, but for it, and we can protrude, let's say, leave the floater sticking out for a meter above the surface. And under those conditions, yes, you could bring a boat alongside, you can climb on top. It might be a bit slimy, but you can deal with that. You can unbolt the hatch and you can climb inside. The issue that we have is that the stability of the machine relies on the tether and on the winch. And so a control system failure on the winch, which for instance causes it to winch downwards whilst you had the hatch off, would risk the machine. If you had a man inside there, you'd risk the man. And so we determined that wasn't a feasible solution. Now that changes for something like the Blue X, which floats on the surface. And so in a calm day, it's going to stay floating stably where it is. But there are others. There are plenty of point absorbers, which I see, photographs of them on lorries with hatches off and ladders going down. And I know that point absorber is reliant on a tension tether with active regulation. And I can't see how you can make a safety case to put somebody inside a point absorber in those conditions. But as I say, everybody's different. So maintainability for us meant that we did have to recover and bring the machine onto the quayside to attend to a number of things. And a lot of what we had to attend to were software related rather than hardware. But unfortunately, the way we had things set up, for instance, we needed to change some of the drive settings in the PTO drive, but we didn't have the interfaces available for us to be able to do that remotely. And so, it was literally a 10-minute software job, but it required a £40,000 recovery and redeployment operation. And that wasn't particularly smart on our part, but it was kind of characteristic of some of the pressures that we were under when we were putting the project together, and the fact that the PTO was, if you like, a completely new system pulled together just for this project rather than a part of a designed product development thing and tested on a back-to-back test rig, which I know that Mocean did, which was something which we would like to have been able to do. So that's maintainability, reliability. All of the major systems on the machine worked extremely well. We didn't actually have any failures. We, apart from, as I say, some software and firmware issues in the PTO drive. So otherwise, we found the thing to be pretty good.
Thank you. I have another question here for both of you as well. So this question acknowledges the challenge with the next step to testing Atlantic wave conditions. And it's asking what the expected size and rating of the full-scale wave energy converter is for these Atlantic wave conditions. Chris, if you want to start, maybe.
I think probably the access at sea is going to be much harder, and we would take into account the design for operations. Because operations are so expensive, our policy generally is that we want to put the machine out at sea and only recover for planned maintenance at long intervals, year-long intervals, 5 years of that order. I think that's the only way that we're going to see significant reduction in operation costs. It's already expensive enough to deploy and recover the machine in the first place, so additional trips for planned or unplanned maintenance are to be avoided if possible. Scaling up the unit power, for us, I think the challenge is going to be devising the right kind of PTO, and we think we're well along with this task. One of the things that we were concerned to do at EMEC at Scapa Flow was to test the viability and efficiency of the PTO that we had. So we didn't have a nominal or an notional PTO in there. We had what we were planning, which is an electrical generator, a low-speed, high-torque electrical generator, and we're measuring the mechanical to electrical efficiencies and the AC electrical efficiencies to DC. For a grid-connected machine, the DC efficiency is less relevant. You're really concerned about the efficiency of the main generator. And the challenge there is that it's going to, if it's direct drive, it's going to be a slow speed machine. So you have to accept that a certain amount of electrical wastage is going to occur. But we think in terms of reliability, this is an easy choice to make. We want essentially to make a machine with just two moving parts, two mechanical moving parts, to which are firmly bolted the two respective moving parts of the generator. So we're striving to make a machine which is as simple as possible and therefore as reliable as possible.
And what did you mention the foreseen rated capacity for that device?
No, I didn't. We commercially, our interests are in supplying energy at the 20 kilowatt level. That's 20 kilowatt continuous power, not peak power. So for small scale marine applications such as offshore electricity supply, for subsea applications or for platform applications, fish farms, small island communities, that kind of application. And for larger, we think a reasonable commercial opportunities in the sub-megawatt. So somewhere between 250 kilowatts and 2 megawatts is a reasonable range to aim for, and that is our present target. And we believe that we can make the appropriate electrical generator for the largest of those machines, the 2 megawatt machines.
Thank you. And Simon as well, about the expected size and rating of the full-scale device for Atlantic wave conditions.
Okay. So that a lot of what Chris has said, I absolutely endorse in terms of operations. And one of the key things for us is that we have to spread the operational cost over as much energy generation as you possibly can. And that means you have to get large if you want to produce machines which have a chance of producing energy at cost competitive with, say, floating offshore wind. For heaving point absorber technology, as far as we can see from our research, you don't get a lot of economic benefit in going above 500 kilowatts per module. And part of the reason for that is there's just a cost benefit curve there. Again, if you go back to what I said about the cost of marine ops, let's say you build a machine which is twice as big as the machine we tested, and let's say the marine ops still only cost you £50,000 for a once a year in and out. That machine, using the very best, using idealized models, might make you just over 500,000 kilowatt hours a year. That is 100,000. That's £100 a megawatt hour just on your unavoidable operating costs. So you've got to get bigger than that, because £100 megawatt hour is not acceptable in the market, and even with the crazy prices we're seeing now. So our approach is, what we're looking at the moment is to increase the generation modules as big as we can, get them up to 500 kilowatts, but also then to integrate a lot of those modules onto a single platform. And the idea of that is that we can then avoid the marine ops for each module, because you make the platform so that it can be accessed either by helicopter or by windcat in the same way as offshore wind is accessed, and that maintenance is then carried out by climbing down inside the machine and operating inside the machine. And so we'd be looking at platforms which could have, we've got designs that could go up to 20 modules, but that'll be a long way in the future. So we're looking at stuff which is multiples of 500 kilowatts, and probably starting at a minimum of 4, based around a single spar buoy as what we're envisaging for the next demonstration project. But we don't actually see there being a feasible way of building a single point absorber. We can design it for Atlantic conditions, but what we can't see is how you can design it for marine operations that can be affordable with the energy that you're going to generate from that size of machine. And that's not wave swing, it's all point absorbers.
Thank you, Simon, and thank you, Chris, as well. I'm afraid we have to stop here, but I suggest that I share the questions with you, Chris and Simon, that we still have, and collect answers by email, and I can put those then on the website on the event page, because there are quite many questions still left unanswered, but I see people dropping off to other meetings already. So it shows that there is a real interest in this topic, and that's great. So thank you very much for joining us today. Thank you, Pablo, Simon, and Chris, for your presentations, and thank you to the audience as well. As I mentioned, the recording will be made available with presentations as well on our website, and I wish you all a very nice evening, and I think it's okay to wish you Merry Christmas already as well. So see you all next year. Thank you. Bye.
Thank you very much.
Thank you.
Thank you, Lotta. Bye.
Bye.